So eventually, let's say you take your solid and put it in your water, and you want to dissolve a lot of, let's say you just want to dissolve a lot of sugar in your coffee, whatever. So you start stirring and stirring and stirring and stirring, adding sugar and adding sugar and adding sugar and stirring and stirring and stirring. Eventually, you can't dissolve any more sugar. It doesn't matter how much you stir, you can't dissolve more sugar. You reach a limit. That limit is what we call essentially the saturation point. You have created a saturated solution. You have dissolved the maximum amount of solute, the maximum amount of stuff, for a given amount of liquid at a constant temperature. Essentially, layman's terms, you've taken all the sugar that you could put into your coffee cup for that particular temperature, and you cannot dissolve a single grain more of sugar. That is a saturated solution. You cannot dissolve any more solute at all. So if saturated is your maximum, unsaturated is any point less than your maximum. Now, that might be a gram less than maximum or 100 grams less than maximum. It doesn't matter. We say that an unsaturated solution is any solution that is under your maximum amount of solute for a given amount of solvent. Again, at a constant temperature. You're going to see this pop up a couple of times. This idea that at a constant temperature, you can be unsaturated or saturated. You can be at your maximum or less than maximum. We'll deal with that in a second, this idea of what would happen if you change temperature. So if saturated is maximum and unsaturated is anything less than maximum, there's also this third state called supersaturated. And if saturated means maximum and unsaturated is less than maximum, supersaturated means above maximum. Somehow you have dissolved more solute than you possibly should have been able to dissolve at a particular temperature. You have to be very, very careful when you make a supersaturated solution. What you have to do is heat it up to a higher temperature, dissolve a bunch of your solute, and then very carefully cool it down. And if you do that correctly, essentially your solution doesn't realize it's dissolved more solid than it should have. I know this is kind of anthropomorphizing a solution, but it's kind of one of the best explanations that there is. I mean, you're tricking the solution into not realizing that it's above maximum. Now, the moment you do something to, quote, make it realize, that could be something as simple as flicking the outside of the beaker or disturbing it in any way, shape, or form, it realizes that it's now over maximum and it'll start spitting out solid until it drops down to saturation. It realizes it's too full and it, kind of just pukes out the extra solid until it goes to exactly as full as it can possibly handle, and all of that extra solid falls out of solution and sits at the bottom of your beaker. Which ties us all kind of together. Notice for all of those definitions, we were talking about at a particular temperature. At this temperature, it can be supersaturated, but at this other higher temperature, that's actually saturation. So it tells us that if you have different temperatures, you can dissolve different amounts of stuff. You can have different solubilities at different temperatures, which means by manipulating your temperature of solution, you can manipulate whether you're unsaturated, saturated, or supersaturated. It all comes down to this idea of temperature. And because you can have changing solubilities with changing temperatures, naturally you can make a graph out of it. So that's what a solubility curve it is. It is a graph that shows the relationship between solubility, how much stuff you can dissolve, per 100 grams of water, or 100 milliliters of water, because remember, 1 gram of water is 1 milliliter of water, and temperature. So we have temperature down here on the x-axis, and we have solubility over here on the y-axis. And essentially, by experimentally determining how much stuff can dissolve at a particular temperature, you can make these nice curves, these nice graphs. You're going to learn how to read. You're going to have to know how to read these graphs and how to understand these certain areas. There's 3 areas on these graphs. Above the line, this is all of my supersaturated solution. So if I were to tell you, hey, you have a solution at 60 degrees, and in that solution you've somehow dissolved 250 grams, well, 60 degrees is right here. 250 grams of solute would be right here, and you could plot the point. And seeing how it's above the line, you could just spit back to me, oh, that's a supersaturated solution. So supersaturated is above the line. Anything below the line is going to be unsaturated. And anything exactly falling on that line is going to be saturated. Everything directly on the line is saturated. So I have supersaturated above the line, saturated on the line, and unsaturated is anywhere below the line. And now we can bring back in this idea of factors and understanding how the factors of temperature, and really temperature, that's what we're going to look at for solubility curves, what else that can tell me, what else I can infer. So as I'm looking at this graph, we can see that as my temperature increases, my solubility is also increasing. So what do I notice happening as solubility as temperature increases? Solubility increases. Well, if I think back to my factors, the phase that increased solubility as temperature increased was a solid. So that tells me that both all potassium nitrate and sodium chloride, all of these compounds are in the solid phase. They're in the solid phase because as I increase, again, temperature, I'm increasing my solubility. It has a positive curve. So with this new graph, with methane and oxygen and carbon monoxide and helium, all of these slopes are negative. They're going down, so as my temperature increases, all of these compounds are decreasing. They're all going down in solubility. Because remember, solubility is over there on the y-axis. So I have a negative slope. Well, if I have a negative slope, well, that tells me that as my temperature increased, my solubility went down. These guys all have to be gases. Because as I increased temperature, I was able to hold less. Essentially, I was increasing the temperature of my soda can. So the real tricky part of 14a is really not that tricky at all. It's just, can you read a graph? Can you plot points on graphs? So let's look at number one. Number one says, how many grams of potassium nitrate can be dissolved in 100 milliliters of water at 60 degrees Celsius? So let's look at the graph. Well, we're talking about potassium nitrate. The formula for potassium nitrate is KNO3. So we're going to be looking at that curve right there. And it wants to know how many grams can be dissolved in 100 milliliters, which is the same thing as 100 grams, at 60 degrees Celsius. Well, 60 degrees right here. So let's look at the graph. 60 degrees. Just kind of go right on up the line. 60 degrees meets the KNO3 curve right about there-ish. And so when I look across, that's going to tell me how many grams I can dissolve. So realistically, somewhere around 102 or 103. I'd honestly even take something around 100 or 105. But all it really is doing is just you reading the graph. You found the temperature at 60, you found where it is on the curve, and you read your line. The next question says, I'll get my eraser here. The next question says, how many grams of potassium nitrate will saturate 100 milliliters of water at 10 degrees Celsius? So again, saturate tells me that I want to be on the line. So 100 milliliters of water, well, this is 100 grams of water, so that's the same thing. At 10 degrees Celsius, well, here's my 10 degrees. I'm still talking about potassium nitrate, so same curve. We follow that curve. It's going to be, somewhere down in here. There's my 10-degree line. It meets right about there. So at 10 degrees Celsius, I don't know, that looks like it could dissolve about 22 grams of potassium nitrate. Okay, so let's look at number 3. Number 3 kind of makes you think about number 1 and number 2 kind of together at the same time. How many grams of potassium nitrate will precipitate, fall out of solution, if I have a 100 ml solution that's saturated? First it's at 60 degrees, and then I cool it down to 10 degrees. So, thanks to question number 1, I know that when a 60-degree solution is saturated, it's 102 grams of potassium nitrate dissolved. I've dissolved 102 grams of potassium nitrate in my solution. When I cool that down to 10 degrees, though, based on my graph, based on my curve, I can only dissolve 22. That's what question 2 had me find. Which means when I take that 60-degree solution and I cool it down to 10 degrees, I have to figure out how much of my solid falls out of solution. My solution can't hold 102 grams when it's at 10. It can only hold 22 grams, which means if I want to know how much would fall out, I just need to know the difference between 102 and 22. So 102 minus 22 tells me that as it cools from 60 degrees to 10 degrees, 80 grams of potassium nitrate will actually fall out of solution. It will stop being dissolved, and it'll be sitting at the bottom of my beaker. Hopefully at this point you've kind of started to get the general gist of some of these questions, but we'll go ahead and answer them all just so that we're all good and happy. We have all the answers that we need. So number 4, get this sorted right. There we go. 100 milliliters of water at 50 degrees Celsius can hold how many grams of ammonium chloride? Well, ammonium chloride is NH4Cl. So at 50 degrees, it can hold about 50 grams. That's what my graph is telling me. 50 grams. Number 5 says 100 milliliters of water at 80 degrees Celsius can hold how much potassium chlorate? Well, potassium chlorate is KClO3, so I'm going to be looking at this line, this curve right there. At 80 degrees, so here's my 80 degree temperature, so I'm going to figure out where those two lines meet. They meet right about there, which means at 80 degrees Celsius, you can dissolve about 40 grams of potassium chlorate in 100 milliliters of water. Next up is question number 6. Yeah, it's question number 6. How many grams of sodium nitrate will precipitate out of a 100 milliliter solution if it's cooled from 80 to 50? So we got to essentially find 2 points now. I'm going to start at 80 degrees Celsius, and I'm going to cool it down to 50 degrees Celsius. Well, sodium nitrate is NaNO3, and at 80 degrees, so here's my sodium NaNO3 line, at 80 degrees, I can dissolve about, 145 looks good, 145 grams. And at 50 degrees, here's my 50 degree temperature, I can dissolve about 115 degrees, or 115 grams. So when I have this solution, it's still not super clear. When I have this solution at 80 degrees, I can dissolve 145 grams. And when it's at 50 degrees, according to my graph, I'm just reading it straight off the graph, right there, I can only hold 115 grams, which means as I cool it from 80 to 50, 30 grams are going to fall out. You're finding the difference between the two. Next up is number 7? Yeah, number 7. If 50 grams of potassium chloride are dissolved in 100 milliliters of water at 55 degrees Celsius, will the solution be saturated, supersaturated, or unsaturated? So at this point, we need to plot a point. We need to figure out a point on this graph based on this particular solution. I know that I have 50 grams dissolved, in 100 grams of water at 55 degrees Celsius. So I have a temperature, 55, oops, I have a temperature, 55, so it's kind of, somewhere right along in there. And I know that I've dissolved 50 grams. Well, 50 grams would be there. So the intersection of 55 degrees and 50 grams is going to be, right around in there. If I want to know what kind of solution this is, well, I'm looking at potassium chloride. I'm going to find the potassium chloride line, KCl. Well, the KCl line is right there. If I compare the point that I drew to the KCl line, I'm above the line. And that tells me that this is a supersaturated solution because the point that I made at 50 grams and 55 degrees is above the line for KCl, potassium chloride. And last but not least, question number 8. So we like questions like number 8 because they're essentially as tricky as it can possibly get. The question says, at 40 degrees Celsius, how much potassium nitrate will dissolve in 500 grams of water? So notice this time, all the other times it's always been in 100 grams or 100 milliliters of water. This time it's at 500 grams of water. Well, if I look over here at my solubility curve, it gives me grams of solute per 100 grams, and every graph we give you is going to always be per 100 grams. But the question wants me to know per 500 grams. Well, if you kind of think through this logically, if I know how much will dissolve in 100 grams, but instead I have 500 grams of water, so 5 times as much water, 5 times as much solvent, I can dissolve 5 times as much solute. So my graph will tell me how much solute I can dissolve per 100 grams. Well, I'm talking about potassium nitrate at 40 degrees Celsius. So 40 degrees, potassium nitrate is roundabouts there. Just for simplicity's sake, we're going to say it's about 60. It's probably a little bit more than 60, like 61 or 2. Well, I guess we can be thorough. So let's say at 100 grams of water, 100 milliliters of water, I can dissolve 62 grams of potassium nitrate. But in my question, it says that I have 500 grams of water. So I'm going to take my 62 and multiply it by 5 because I have 5 times much solvent. I can dissolve 5 times as much solute, which, if my math is right, tells me I can dissolve 310 grams of potassium nitrate. Again, 5 times as much solute means 5 times as much solvent. So there you go, solutions and solubility curves, learning target 14A, done.